This week we have learned about tunnel diode theory more deeply than last week's lecture. First, we had learned about Isaki diode. It was first invented by Leo Isaki in 1957, which is the first quantum electron device. What we have to focus on this section is NDR, which is an abbreviation of the negative differential resistance. This. It means when the voltage increases, the current will gonna decrease. Actually, the value on this graph is not the negative, but when we difference this value, it will gonna negative value, so we call it negative differential resistance. For next section, we will concentrate on the degenerated semiconductor. As you can see in this diagram, if the difference between Fermi level and conduction band is bigger than 0, it would be degenerate state. And also, such highly doped semiconductors are called degenerate semiconductor. It is some kind of very bad device if the semiconductor is degenerated state. And if the difference between Fermi level and conduction band is smaller than the 0, we call this state as non-degenerated state. For next section, seeing this diagram, if the forward bias is given to the PN junction, as the voltage is increasing, electrons would go through the PN junction barrier, and the empty hole state in the p-type valence band will gonna be aligned with the n-side stage, which is in the conduction band, and finally, electrons would fill the empty stage. As the voltage is keep increase, this stage will gonna misalign, and through this result, current begin to drop. We call this phenomena as negative resistance because as the voltage increase, current will also decrease. If the voltage is keep increasing, the diode will gonna operate as the normal diode. If the reverse bias here is given to the device, tunnel diode will be called as back diodes, and it acts as like a very fast operating rectifier, and it will show the extremely linearity concerning power signal. And under the reverse bias condition, state which is filled in the P side will gonna align with the state in the n side which is empty, and electrons will gonna go through the p-n junction barrier in the reverse direction. And for next section, I would like to review about IV characteristic of tunnel diode. And it is some kind of theory that I talked before this part. It's usually same, but this time I would like to explain more specifically. Under the thermal equilibrium state, no current will gonna flow if a small forward because no bias is on the p-type and n-type, n-side and p-side. If a small forward bias is given to the device, electrons in the conduction band of the N region will tunnel to the empty stage of the valence band in P region here, because the Fermi level is higher than the P side valence band. So it is very easy to tunnel through. If the forward bias is given, until maximum tunneling current. Electrons in the n-side conduction band will tunnel through the p-n junction barrier until the current reach peak point here. Further, if the forward bias is given after maximum tunneling current, as voltage increases, current will start to decrease. As the empty stage decreases because of the electrons tunnel from n-side conduction band, we call this region as negative differential resistance because it has negative value when we difference them. What we have to know in this part is that there is still a tunneling current, but each amount is decreased compared to previous state. If the forward bias is given after valley, there will be no tunneling current and diffusion current is start to grow. As the n-side Fermi level is increased here and become near the p-side conduction band, electrons will gonna start to flow the p-side conduction band because the Fermi level of the conduction band is getting near to the conduction band of the p-side. For large forward bias is given to the p-n junction, more current will gonna diffuse to the p-side conduction band. And for this reason, as the voltage increase, current will gonna rise very strictly. And under reverse bias, it will operate opposite to the forward bias case that I talked before. And for this section, it is same as that I talked before. The total current here is consists of tunneling current and diode current and excess current. And as you can see here, the diode current is same as the normal diode current. We don't have to memorize these equations. We have to know how to use it. And we had learned about resonance tunneling diode, and it is consist of two barrier, and this is how it operate. And thank you for listening.